Hi everyone, in this lecture I'm going over materials of chapter 8, graphs. In this lecture we basically cover the preliminary definitions of graph theory. So we start this lecture by defining an undirected graph. Previously we had defined a directed graph when we were talking about binary relations. So in this chapter, we define an undirected graph in a general form. An undirected graph is an ordered pair of two sets. The first element in this ordered pair is V, which is the vertex set, and the second element is the edge set. V, which is the vertex set, is the set of all vertices in the graph, and E is the set of all edges in the graph. As I said, an undirected graph can be defined in the similar way as directed graphs. However, the edges in undirected graph are not directed edges. What does it mean? It means that the edges are unordered pair of vertices. They aren't represented by ordered pairs anymore because they are not directed. So this kind of graphs is useful for modeling relationships that are symmetric, which means that if A is related to B, B is also related to A. So there's no need to have a directed edge between A and B when the relationship is symmetric. Every element of vertex set V is called a vertex, and it is usually represented by a dot with a label. For example, in this graph, we have 5 vertices, A, B, C, D, and E. As you see, every vertex is represented by a dot with a label. This is an undirected edge between A and B. And the way of representing this edge is to use the set roster notation and write A comma B, because if you remember, in the set roster notation, the order of writing elements doesn't matter. That's why we use it for undirected edges. However, if you remember, when we wanted to represent a directed edge, we were using an ordered pair of A and B when the arrow goes from A to B, and that's because in a directed edge it matters what the first element or what the first vertex is and what the second vertex is, because the edge is directed and it is represented by a directed arrow with an arrow pointing to B, toward B. So it matters what the first and second endpoints of a directed edge is. That's why we don't represent it with a set like this. But in an undirected edge, you can represent the endpoints by a set roster notation like this. So if you replace A by B and B by A, you still have the same edge from A to B, because the line segment that you see between A and B has no arrows on it. So here is an example of two graphs with the same set of vertices. This is the first example when you have 5 vertices A, B, C, D, and E, and A is connected to B by an edge, E is connected to D by an edge, and C is connected to D by an edge. And then this is another graph with the same exact set of vertices. However, this graph has no edge set. So the edge set in this graph is equal to the empty set. Then we define parallel edges. Parallel edges are multiple edges between the same pair of vertices. So if two or more edges have the same endpoints, they are called parallel edges. A graph can also have a self loop, which is an edge between a vertex and itself. So in this graph, as you see, there's a self loop from C to itself, and there are two parallel edges between A and B, because as you see, both of these two edges connect A to B, so they have the same set of endpoints. That's why they are called parallel edges. If a graph does not have a parallel edges or self loops, it is called a simple graph. This is a simple graph because you cannot find any self loops or parallel edges in this graph. Let's talk about some terms in graph theory. If there is an edge between two vertices, those vertices are called to be adjacent vertices. And then vertices B and E are the endpoints of an edge like this. So if you represent an edge using a set-Raster notation like this, it means that it connects B to E, and B and E are called the endpoints of that edge. The edge B and E is incident to vertices B and E. So the word incident is used in this context. When an edge connects two edges, when an edge connects two vertices, it is incident to both of those vertices. Next, we define a neighbor. We say a vertex C is a neighbor of vertex B if and only if the edge B and C exist in that graph. Now, in a simple graph, the degree of a vertex is the number of neighbors it has. What do we mean by simple graph? We defined it in the previous slide. A graph with no self loops and no parallel edges. The total degree of a graph is the sum of degrees of all the vertices in that graph. So what was the degree of a vertex? The number of neighbors of that vertex. It means the number of vertices that are connected to that vertex. And then the total degree of a graph is the summation of all the degrees of all the vertices in that graph. If you have an undirected graph like G with vertex set V and edge set E, then twice the number of edges is equal to the total degree, which means that if you add all the degrees of the graph, all the degrees of all the vertices in the graph, the summation would be equal to twice the number of edges, twice the cardinality of the edge set E. This is a famous theorem that can be proven, but we don't prove it in this course. The next terminology that we introduce in this lecture is regular graphs. When we say a regular graph, when we say a graph is regular, we mean all the vertices have the same degree. Then we define deregular graph. We say a graph is deregular if and only if all vertices have the same degree equal to d. So, for example, a two-regular graph is a graph in which all vertices have degree 2, which means every vertex has 2 and only 2 neighbors. Also, we define a subgraph for a graph in the following way. We say a graph like H with the vertex set VH and edge set EH is a subgraph of graph G with the vertex set VG and edge set EG if the vertex set of H is a subset of vertex set of G and the edge set of H is a subset of the edge set of G. So if G is this graph, by removing an edge like E from this graph and removing the edge between E and B and E and D and the edge B and C from this graph, you will get graph H as that you see in this figure. So graph H has a vertex set that is a subset of vertex set of G, because H has only 4 vertices while G had all the 5 vertices. And H has only 3 edges, and these 3 edges are subset of the edge set of G. As you CG has 6 edges, that 3 of them are the ones that H has. So the edge set of H is a subset of the edge set of G, and the vertex set of H is a subset of the vertex set of G. That's why we say H is a subgraph of G. Also, if you remember, I was talking about regular and irregular graphs. This graph is not a regular graph because the degree of C is 4. There are 4 neighbors for C, which are A, B, E, and D. But there's only one neighbor for D, which is C. So degree of D is 1, degree of C is 4. They're not equal. Therefore, this graph doesn't satisfy the definition of a regular graph, which means all the degrees have to be the same. This graph, however, is a regular graph. Basically, it is a 2 regular graph because the degree of every vertex is equal to 2. This graph is called a polygon. This graph is a 4 regular because every vertex that you pick has degree 4, which means every vertex in this graph has 4 and only 4 neighbors. Next, we define a complete graph or a clique. Kn, K with subscript n, is called a complete graph on n vertices, where n is a non-negative integer. I'm sorry, where n is a positive integer, not non-negative, which means n can be as low as 1 and it can be any other positive integer. Kn has an edge between every pair of vertices, which means that every pair of vertices that you pick in graph Kn, they have to be neighbors. They have to be adjacent. Kn is sometimes called the clique of size n or an n clique. This is an example of a clique of size 6. As you see, there are 6 vertices in this graph, and every 2 vertices that you pick are connected by an edge. Then we define K sub m comma n, which is a complete bipartite graph on 2 disjoint sets A and B of m and n vertices respectively. So it has a total of m plus n vertices. The first m vertices belong to set A, and the second and the other n vertices are part of or are the elements of set B. K, m, and n has an edge between every pair of vertices, one selected from A and the other from B. So if you select an element or a vertex from A and select another vertex from B, those vertices has to be adjacent. There should be an edge between them. Also, it has no edge between vertices of A, and it has no edge between vertices of B, which means among the set of vertices A, there should be no 2 vertices that are neighbors. So none of the vertices in set A are neighbors. Also, none of the vertices in set B are neighbors. Let's see an example of K, 3, and 4. 3 and 4 means the first set A has 3 vertices and the second set B has 4 elements. So as you see, there are 3 dots here representing the 3 elements of A. There are 4 dots here representing the elements of B. As you see, none of these 3 are neighbors. There's no edge between any of 2 elements selected from this set. And there are no 2 elements in this set, in set B, that are neighbors. However, every vertex that you pick from the first set, from A, and every element that you pick from the second set, which is B, are connected by an edge. That's called a complete bipartite graph on a set of size 3 and 4. There are many ways to represent a graph. One of the most famous ones is to use the adjacency list. In the adjacency list representation of a graph, every vertex has a list of all of its neighbors. For example, in this graph, which we have 5 vertices, A as the first vertex keeps a list of its neighbors B and C. B keeps a list of its neighbors A, C, and E. C keeps a list of its neighbors A, B, and D. D keeps a list of its neighbors C and E. And E keeps a list of its neighbors B and D. So if you want to find out whether B and C are neighbors, what you can do is you can traverse the adjacency list of B and see whether you can see the letter C in it. As you see, letter C is in the adjacency list of vertex B. Therefore, we say B and C are neighbors, or B is adjacent to C, or C is adjacent to B. Another representation of a graph is to use a matrix, a square matrix with n rows and n columns. So if you have n vertices, then the matrix representation has size n by n. And the entries of this matrix are either 0 or 1, indicating whether or not each edge is present in the graph or not. For example, there is no self loop from 1 to itself. Therefore, this entry in the first row and first column is 0. 2 is connected to 3 by an edge. That's why in column number 3 and row number 2, the value of the entry is 1, which means there's an edge present in the graph that connects 2 to 3. For the same reason, there's the third row and second column has a entry equal to 1 because there's an edge from 2 to 3. In the same way, you can fill out the whole matrix. This matrix represents this graph. So this is the geometric or visual representation of the graph. This is the matrix representation of the same graph. Next, we define isomorphism for two graphs. We say graph G equals V and E and G prime equals V prime and E prime are isomorphic if there is a bijection like F between the vertex sets of these two graphs, such that for every pair of vertices like X and Y in graph G, if X and Y are neighbors in G, then their images by F, which are f of X and f of Y, are also neighbors in G prime. So if X and Y are neighbors in G, their images, which are f of X and f of Y, are also neighbors in the other graph, in G prime. And vice versa, which means that if their images are neighbors, they have to be neighbors too in graph G. So X and Y is in the edge set E if and only if f of X and f of Y is in edge set E prime. The function f in this definition is called an isomorphism from G to G prime. Let's assume that we are given two graphs, G1 and G2. As you see, they both have 5 vertices and they both have 6 edges. And you see that there's a bijection between the vertex set of G1 and vertex set of G2. This is the bijection. A is mapped to 4, B is mapped to 3, C is mapped to 2, D is mapped to 5, and E is mapped to 1. So assuming that we are given this bijection, you can see that the image of A and B in graph G2 are neighbors, in the same way that A and B are neighbors in G1. So A and B are neighbors in G1, and their image, which are 4 and 3, are also neighbors in G2 in the red graph. In the same way, B and C are neighbors in G1, and their image 3 and 2 are neighbors in G2. Same for C and E, E and D, A and D, and B and D. So as you see, if you map the vertex set V1 to V2, the edge endpoint relationship between in both graphs G1 and G2 are preserved, which means that in graph G2, the images of the neighbors in G1 are neighbors. Next, we define a walk between two vertices in a graph like G. We say a walk from V0 to VL in an undirected graph G is a sequence of alternating vertices and edges that start and end with a vertex. So here is a walk from V0 to VL. We start from V0, the source of the walk, and then we write down an edge, because as I said, a walk is a sequence of alternating vertices and edges, which means after a vertex we need to have an edge, and after an edge we need to have a vertex. The edge after V0 connects V0 to V1. Then we have a vertex V1. Then we have an edge starting from V2 ending at starting from V1 ending at V2. Then we have vertex V2. Then we should have an edge, then vertex, edge, vertex, all the way to V sub L minus 1, and the edge connecting V sub L minus 1 to V sub L. And finally, we have a vertex called VL as the last vertex or destination of the walk. The vertices just before and after each edge are the two endpoints of that edge. For example, V1 and V0 are the endpoints of the edge at the middle. For a simple graph, since the edges in a walk are completely determined by the vertices, you can represent a walk by only the sequence of vertices. So you can ignore the edges. Just write all the vertices if the graph is simple. Why? Because if the graph is not simple, then you may have loops. You may have parallel edges, and if you have parallel edges, then there may be more than one edge between two given vertices. Next, we define the length of a walk. The length of a walk that you see here is equal to L, which is equal to the number of edges participating in this walk. Next, we define an open and a closed walk. An open walk is a walk in which the first and last vertices are not the same. So if V0 and VL are not the same, then that walk is called an open walk. If they're equal, if the first and last vertices are the same, then we call that walk a closed walk. Look at this graph. In this graph, we can find a walk of size 5, a walk of length 5. How? Since we have a simple graph, so all we need to do is to write down the vertices or the sequence of vertices participating in this graph. So we start this walk from A, and then we go to E, then C, then B, then E, and then finally A. So this is a walk and this is a closed walk because we start from A and we end up at the same vertex A. Next, we define the special cases of a walk, which is a trail, a circuit, a path, and a cycle. What is a trail? A trail is an open walk in which no edge occurs more than once. So a trail is an open walk with no repetitive edges. What is a circuit? A circuit is a closed walk in which no edge occurs more than once. So a closed walk with no repetitive edges is called a circuit. What is a path? A path is a trail in which no vertex occurs more than once, which means that a path is a trail with no repetitive vertices. So if you remember, we said a trail is an open walk with no repetitive edges. That means we can say a path is an open walk with no repetitive vertices and edges, which means a path is like an open walk, but repetition of vertices and edges are not allowed. Finally, we define a cycle. A cycle is a circuit of length at least 1 in which no vertex occurs more than once, except the first and last vertices, which must be the same. So other than first and last vertices, a cycle must not have any repetitive vertices. So a cycle is a circuit with no repetitive vertices, but a cycle must have the length of at least 1, which means it should have at least one edge in it. So here is an example of a circuit. The circuit starts from E, and then it goes to B, C, E, F, A, E. So as you see in this circuit, we have repeated vertex E 3 times, but it is still a circuit. Why? Because we didn't repeat any edges. We have repeated vertices, that's why this circuit is not considered to be a cycle. But it is a circuit because we didn't repeat any edge in this walk. So this walk is a circuit because it's a closed walk and it has no repeated edges. This circuit is not a cycle because vertex E occurs at the middle as well as the beginning and the end. Next, we define graph connectivity. In an undirected graph, if there's a path from vertex V to vertex W, then there is a path from W to V2, which means if there's a path from one point to another, there should be another path in the opposite direction. The two vertices V and W are said to be connected. A vertex is always considered to be connected to itself. So if there's a path between any two vertices in a graph, those vertices are called to be connected. And obviously a vertex is always connected to itself because there's a path of size 0, of length 0 from that vertex to itself. A graph is said to be connected if every pair of vertices that you pick in that graph are connected, and it is disconnected otherwise. So when do we say graph is disconnected? If you can find a pair of vertices for which there's no path from one vertex to another. A connected component is a maximal set of vertices that is connected. So if you have a graph, a connected component is a set of vertices that are connected, and that set is maximal. What does maximal mean? It means you cannot find any other set of vertices that are connected and contain this set of vertices. It means it is not expandable. You cannot make that set of vertices larger and keep it still connected. A vertex that is not connected with any other vertex is called an isolated vertex. So if you have a vertex that is not connected to any other vertices in that graph, then we call that vertex an isolated vertex, and therefore that isolated vertex would be a connected component by itself with only one vertex, which means that isolated vertex creates a connected component because you cannot add vertices to it and keep it still connected. Any vertex that you add to that vertex, you make it a disconnected graph. So a vertex that is isolated by itself creates a connected component. Next, we define a Euler circuit in the following way. A Euler circuit in an undirected graph is a circuit with a specific condition. What's the condition? The condition is it should contain every vertex and every edge. So since it is a circuit, it should not have repeated edges, and since it is a Euler circuit, it should contain all the edges. So every edge should be in a Euler circuit exactly once, which means one and only one time. So this is a graph with 6 vertices A, B, C, D, E, and F. The following closed walk is called the Euler circuit. We start from A, and then we go to C, D, B, F, C, B, A, D, E, and finally we go back to A. It is a closed walk because we start at A and we finish at A. It is a circuit because no edge is repeated more than once. And it is a Euler circuit because every edge is participating in this circuit. And obviously, if every edge is participating in a circuit, it means that every vertex is also participating in that circuit. Now, there's a necessary and sufficient condition for having a Euler circuit. An undirected graph G has a Euler circuit if and only if G is connected, and every vertex in that graph has an even degree. For example, in this graph, edge E has degree 2, edge A, B, C, and D, they all have degree equal to 4, and edge and vertex F has degree 2. So all the vertices have even degree. 2 here, 4 here, 4 here, 4 here, 4 here, and 2 here. So since all the degrees of all the vertices in this graph are even, we can say that graph should have a Euler circuit. And that's an example of a Euler circuit in this graph. If even one of the vertices doesn't have an even degree, then that graph does not have any Euler circuits. In a similar way that we define the Euler circuit, we define a Euler trail. A Euler trail is a specific trail, is an open trail that includes each edge exactly once. So look at this graph. We have again 6 vertices A, B, C, D, E, and F, but we have different edges this time. So the following open trail is a Euler trail. We start from B, and then we go to F, C, then we go back to B, then we go to A, then C, then D, then A, then E, and then finally we go back to D. So we started from B and we ended up at D. Okay, so it's not an open, it's not a closed walk because the first and last vertex are different. It's an open walk, and it's a trail. Why is it a trail? Because there is no repeated edges in this walk, and it is called the Euler Trail. Why? Because every edge is participating in this trail. So let's look at the degrees of vertices in this graph. Degree of E is 2, degree of A is 4, degree of C is 4, degree of F is 4. I'm sorry, degree of F is 2. So far, all the degrees are even. However, degree of B and degree of D are both equal to 3, which are 2 odd degrees. So since not all the vertices have even degrees, this graph does not have a Euler circuit. But this graph, as you see, has a Euler trail. There is a necessary and sufficient condition for a graph to have a Euler trail. And this is the condition. An undirected graph has a Euler trail if and only if that graph is connected and has exactly 2 vertices with odd degrees, which means all other degrees are even except 2 vertices that have odd degrees. In this graph, as you see, B and D have odd degrees. The other vertices have even degrees. So there should be an Euler trail in this graph, and that was the trail that I showed it to you. Finally, we define a Hamiltonian cycle and Hamiltonian path. A Hamiltonian cycle in an undirected graph is a cycle that includes every vertex in the graph. So what was the definition of a cycle? It was a closed walk with no repetitive edges and vertices. Now, a Hamiltonian cycle is a cycle, which means we cannot have repeated vertices or edges, but it has to include every vertex in the graph. What is a Hamiltonian path? A Hamiltonian path in an undirected graph is a path that includes every vertex in the graph. So since it is a path, it cannot have repeated vertices or edges. And however, since it is Hamiltonian path, it should have every vertex exactly once. So it cannot have repeated vertices, but it has to include every vertex one and only one time. So let's look at a Hamiltonian cycle. This is an example of a Hamiltonian cycle. In this graph, we start at X, then we go to V, W, Y, Z, and then X. So it's a closed walk because we start and end at X. It has no repeated edges, no repeated vertices, therefore it's a cycle. And it's a Hamiltonian cycle because it has traversed all the vertices in this graph. On the other hand, this is an example of a Hamiltonian path. We start from X, then we go to V, W, Y, and Z. It's an open walk with no repetitive edges or vertices, therefore it's a path. And it's a Hamiltonian path because every vertex is traversed by this walk. So this is an example of Hamiltonian cycle. This is an example of Hamiltonian path.